Another way we can think of slope is as a rate of change. And this happens to come in more commonly with applications and word problems. And rate of change is the exact same thing as slope. But it just tends to be used for more applied words, and it's just a change in verbiage. So how fast is y changing with respect to x? So how much is that vertical change occurring compared to the horizontal change? Again, we're looking at the same thing here, but the idea of rate of change can apply to a lot more cases than just plain old linear examples. So we tend to change the wording a little bit. So here's one example of an application. At one part of the road to the summit of Pikes Peak, the road rises at a rate of 15 vertical feet for a horizontal distance of 250 feet. Find the grade of the road. And a grade of the road is another way actually to say slope or rate of change. If anybody's ever been driving near the mountains, I know sometimes when I go to New Hampshire, I see all these signs on the road, and they're typically yellow signs. And in the picture, it'll have a truck kind of showing you like riding up a hill or down a hill. And then there's a number in it. And that number is typically a percentage. And it's a warning that you're coming to a very steep part of the road. So even if the percentage may seem small, like 7%, it's actually, again, going to be a much steeper either climb or descent compared to what you've been driving on. So we do talk about road quite a lot. The steepness of a road is really important for safety reasons, and for parking, for driving, etc. And it typically is given as a percent. So what we're going to do is we're going to find the grade of this road, and then we're going to change it to a percent. Now, we have lots of formulas for slope, but the one that works really best for applications is just the basic idea of vertical change to horizontal change. So in this case, my vertical change is 15 feet and my horizontal change is 250 feet. Now you would still want to simplify that fraction. So I can divide these both by 5. So I would have a 3 on top and a 50 on bottom. So in slope form, this is 3 to 50. And what this means is that for every 50 feet that you travel, horizontal distance, you're increasing or decreasing by 3 feet. Depending on which way you're driving, right? One way you could be going uphill, one way you could be going downhill. Typically for applications, we tend to use the positive version if it could go either way, right? Depending on which side of the road you were on. We usually just leave it in the positive form, but do know that that could mean that you're decreasing and not increasing as well. So this would be 3 out of 50. Now, it is pretty common for grade to be written as a percent. And if you haven't seen percent in a while, you want to remember that percent is always out of 100. So what you really want to do is you want to get your denominator to be something out of 100. And we can do that pretty easily here by multiplying by 2. So 6 out of 100 would be the same thing as 6%. Now, if you don't have an easy calculation here, I'm just going to take out my calculator for a second. We can also convert to percent a different way. Now, here was pretty easy to go from 50 to 100. But let's say, it wasn't. What you could do is on your calculator, do 3 divided by 50, get that decimal form. And then what you do is you move your decimal point 2 spots to the right. So that's another way that you can get a percent form. So if your numbers are much more complicated and you're like, I can't think of an easy way to get to 100, then just divide. And then you're going to move your decimal point 2 spots to the right. And you can see that that changes this into just 6. And again, there is your percent. So that's how you can convert to a percent for some of these problems. So the answer here then would be 6%. Now, another application that I want to talk about would be the pitch of a roof. And again, it's just a change in language here. Pitch is really another way to think of slope or your rate of change. So here's just a little picture of a house that I drew. And let's say that, at the peak of the roof, it's 7 feet tall. And then there's a horizontal distance on the left here of 10 feet. So you can find the pitch of that roof. Again, it's going to be vertical change over horizontal. It would be 7 over 10 here. And if I could simplify that fraction, I would, although I can't. So at least on the left side of the roof, because not every house has symmetric roofs, right? That piece right here has a slope or a rate of change of 7 to 10, meaning for every 7 feet it increases, there's 10 feet long that it's going to travel. And again, there's lots of other applications here. So ramps are another important one. There's a lot of regulations around wheelchair ramps, for instance, and things like that. So really a ton of applications with slope and rate of change beyond just, linear lines, which also have plenty of applications too. But just going a little bit outside the box here and a little bit more real world for a moment. Now I want to jump to one more example here of an application. And again, there are so many of them, but I just want to show you something a little bit different as well. So here's an example where what we have is that this graph shows the worldwide production of fresh fruit in millions of metric tons for year X. So on the X-axis, you have years, and along the Y-axis, you have fresh fruit production, and this is in millions of metric tons. And you have two data points here that you're given. And the first question asks you to find the slope of the line and use proper units for the rate of change. Again, because they actually are units here, right? So it's not just a generic equation, it actually has meaning. Now, when we do slope, don't forget we use that formula, that y2 minus y1 over x2 minus x1. So what they're doing here is they're plugging that in. So they're using the formula that looks like this, and they're plugging in our values for our points. So you can see on the top, they're subtracting the y values, and on the bottom, they're subtracting the x values. They get 147 out of 10. Now, a lot of times we do sometimes use decimals. So we do love fractions for slope most of the time. But when you're dealing with real world applications, 147 out of 10 is not super helpful always when understanding things. So we do sometimes convert to the decimal form. And we do that just by dividing here. So what they did is they divided 147 by 10. That gave you 14.7, which is a number. Now, you can always have a denominator of 1, though, and that is actually something we typically do with slope with real-world applications, is we'll divide this, and if we divide both top and bottom by 10, you are still left with that 1 in the denominator. Now, the other thing that I want to point out here are the units. Now, the top values when you subtract are your y's, and the bottom are your x's, so the units should match up that way. Notice for my y values, the units are millions of metric tons, whereas for my x values, the units are years or time, right? So you can see that's how they match up the units, and that is super important. Your y unit stays on top, and your x unit goes in the denominator. So now to interpret this, if you have your units set up in the correct spot, it's actually really easy to write a sentence to interpret this. So this means that the rate of change of worldwide production of fresh fruit is 14.7 million metric tons per 1 year. We can also say 14.7 million metric tons per year. So that slash there often means per, and if there's no number afterwards, it's always implied to be a 1. But we can translate this to sentences, but it's really important that you use your units and make sure they're in the correct spot. So y unit on top, x unit on bottom, and then it should read pretty clearly. And again, the other thing we do often do is we often do divide this out so that you have a 1 in the denominator. And again, it just makes it sometimes easier to understand how things are changing on a yearly basis rather than on every 10 years, right? So here I can understand what's happening in 1 year versus 10 years. So we do like to have that 1 year piece there as well. And again, underneath that too, you can see another example here. Very, very similar, looking at the cost of laundry. 2 points are given, so we can find that slope, again, just by using our formula and then watching the units. So here I want to point out the Y units are dollars and the X units are pounds of laundry. So when you get your final answer, you're comparing dollars per pounds of laundry. So again, it's really important just to watch those units and have them set up in the correct spots.